Let's start the lecture portion, and then I'll go over the test real quick when we're done with the lecture. That's not the marker. That's the marker. Okay. So the next section introduces two different ways of proving. So thus far, we've been doing what's called a direct proof. You've been showing that if alpha is true, then beta is true, as a general rule, where alpha and beta are statements, right? If x and y are even, then x plus y is even, type proofs. So when you prove it directly like that, we call that a direct proof, when you just think about it in terms of alpha implies beta. Well, there's two other ways of thinking about that same idea, alpha implies beta, that sometimes there's two logically equivalent ways of thinking about alpha implies beta that sometimes make it easier to prove something. Sometimes a direct method seems kind of hard to think about that way. Those two ideas are going to be proof by contrapositive and then what's called a reductio ad absurdum proof, or a proof by contradiction. So we'll go over each of these and see how they're logically equivalent to alpha implies beta, and I'll do an example of each of them. So, first one we're going to do is called proof by contrapositive. So instead of showing that alpha implies beta, we show that not beta implies not alpha. So first let's wrap our heads around this logic, and then we'll do a proof to see it's the same thing. So alpha implies beta, when was that true?
When alpha's true.
Alpha's true. That's true. What about this one?
True.
Alpha is true, beta is false, so alpha implies beta is
False.
False. Alpha is false, beta is true, gives
True.
true. False, false gives
True.
perfect. So now let's think about this one, the contrapositive. Not beta implies not alpha. So here's not beta, here's not alpha, so you didn't have to look all the way over here and try to really think about it. So false implies false is
True.
true implies false is
False.
false implies true is
True.
true implies true is
True, sorry.
true, right? And true, false, true, 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 false, true, true. Logically equivalent, right? And don't worry about that last one for now. So, thinking about it this way is logically equivalent to thinking about it this way, but what does that mean? Not beta implies not alpha. So let's do an example where we do the contrapositive. So, let R be an equivalence relation on a set A, and let A and B be two elements in A. We're going to prove that if A is not related to B, then their intersection is the empty set. The intersection of their equivalence classes is the empty set. This is something we already did. So, re-wrap your head around what we're saying here. Grab two elements. If A is not related to B, then they're in different equivalence classes. If A is not related to B, the intersection of their equivalence classes is the empty set.
Isn't that obvious?
Yeah, this should be pretty obvious to you. We're doing kind of an obvious proof to introduce contrapositive. The point isn't wrapping your head around this, it's going to be how you do a contrapositive proof. So what's the contrapositive of if A is related to B, then this intersection is 0. Here's your alpha, here's your beta. If alpha, then beta, we're going to show that not beta implies not alpha. So we're going to assume not beta, assume A intersects B is not the empty set, and we're going to show that that implies not alpha, or A is related to B. So instead of showing if A is not related to B, then their equivalence classes have nothing in common, we're going to show that if their equivalence classes have something in common, then A is related to B. Those are logically equivalent ways of thinking about it.
Okay.
Okay? That's the leap there. How I actually do this proof isn't a big deal, but make sure you can wrap your head around that. You can look at a statement and state it's contrapositive. Let's just do word examples for a second. Maybe that will help. If I go to the store, then I'll buy a steak. What's the contrapositive of that?
If I don't buy a steak, then I didn't go to the store.
Perfect. If I don't buy a steak, then I didn't go to the store. Alright. If I'm standing in the classroom, then I'm the teacher.
If you're not the teacher, then you're not the classroom.
If you're not the teacher, then you're not standing in the classroom. You're sitting, is what I think he is,
Yes,
right?
I understand.
Just you see how those are saying the same thing? Making that leap in your head?
Yeah.
That's the leap that you need to make, is how to think about the contrapositive, and then the proof is just how you've always been doing the proof. So, if not this, then not this is what we're doing. So, assume not beta. Assume that these equivalence classes aren't the empty set, or in other words, they have some element in it. So, assume that the equivalence class on A intersected with the equivalence class on B is not the empty set. Then there exists some element in this set, right? And if X is in the intersection of that set, that means X is in the first one and X is in the second one. That's what intersection means, right? So since X is in the equivalence class on A, we have X is related to A. And since R is the equivalence relation, we can use the reflexive property to get A is related to X. And since X is in B, we have X is related to B, right?
Right.
So A is related to X and X is related to B. And by the transitive property, A is related to B. We're done.
Kinda didn't make sense.
What part didn't make sense? You good up to here?
I'm not sure what we're trying to prove here.
So what we're trying to prove is that if A is not related to B, R is the equivalence relation, right? It's reflexive, symmetric,
I see
transitive.
what you did. Okay, never mind.
Oh, so you all good now?
Yes.
Good? Okay? Alright, so that's the idea of contrapositive. Alright, the other idea is a reductio ad absurdum argument. Yes, reductio.
I thought you were just missing an N.
Nope, reductio ad absurdum. So this is a general type of argument that's used in arguments in general. I guess the best way to say that.
Okay.
Here's the way that this argument works. If this argument leads to an absurd conclusion, then the premises of that argument are false. I'd say that again. If an argument leads to an absurd conclusion, then the premises of the argument is false. If I have, if some statement, then Donnie is a purple elephant, that statement must have been false. Because Donnie is a purple elephant is obviously not true. Does that make sense?
Okay.
Another way that we think about proving the truth of these statements is we show it's impossible for the statement to be false. Therefore, the statement has to be true. That's another way that you can view it. We show that A being true and B being false leads to something that's obviously false, impossible. Okay? If we can show that A being true and B being false leads to something that's impossible, that's the same thing as showing A implies B. So let's think about that in terms of this one for a second, since we just did this one. So A would be A is related to B, and not B would be their intersection is not the empty set.
Wait, that,
Right? So if A is not related to B, then their intersection is not the empty set. Is it impossible?
Oh.
I mean, so that's impossible. It's impossible for us to have alpha and not beta. I mean, so that implies something that's false. Something that's impossible. Something that's absurd.
Right.
Okay? So, alpha and not beta implies false is the same thing as alpha implies beta. So let's see with the truth table real quick. I wrote out alpha and not beta real quick for you here. So we have alpha and not beta. False, true, false, false, right?
Yeah.
No.
True and false is false. True and true is true. False and false is false. False and true is false.
Wait.
Alpha and not beta. Alpha, that's beta, that's not
Oh,
beta.
you're saying they mean the same
Well, I'm just writing this out. This is what I'm going to say is the same thing.
Oh.
So now let's look at this one. Alpha and not beta implies false. So false implies false is
Oh, true.
true.
Right.
Wait a minute.
True implies false is
If false implies false is true, then one of those, then right there, that should be true.
false implies false, true.
No, false implies false, is false.
This is false and.
Oh, okay.
Okay. Alright, so back to this one. So false implies false is true. True implies false is false. And then false implies false is again true. False implies false is again true. So there's the truth table. To show that alpha and not beta implies false has the same value as alpha implies beta. They're logically equivalent. The thinking behind it is to show that alpha implies beta. You show that alpha and not beta is impossible. It leads to something that's absurd.
Hang on.
Okay.
It implies something that's obviously false.
This doesn't make sense.
Does this column make sense?
Awful.
Okay, so let's start with this column.
Now look. True implies false is true. Except we switch it up there, so
True implies false is false.
implies false is false.
Implication,
And then the second row down, is that true implies false?
look, implication is only false when you have true implies false.
Why not?
Right? So over here, looking at this, we have false implies false is true. We have true implies false is false. We have false implies false is true. This is the value we're plugging in for this expression. Good? Quicken? So you see how this is logically equivalent to this?
Yeah.
Okay, so let's see a proof by contradiction. So we're going to prove that no integer is both even and odd. Okay? The way that we show this is we're going to show that it's impossible for an integer to be both even and odd. So we assume that there's an integer that's both even and odd and show that that's impossible. It leads to something absurd. It leads to something impossible.
So what's BWOC?
Say that again?
What's BWOC?
By way of contradiction. So here's how you read this. Assume by way of contradiction that there is some integer such that x is both even and odd. So assume that there is an integer that's both even and odd, and we're going to lead to something that's impossible, or what we call a contradiction. Okay? So just follow the logic here. So assume by way of contradiction that there exists some integer x, such that x is even and x is odd. Let's assume that this isn't possible for a second. Since x is even, 2 divides x, right? Which gives us that there exists some integer a such that x equals 2a. Since x is odd, then there exists b such that x equals 2b plus 1. Right? With me so far? Then, x is obviously equal to x, which gives us 2a is equal to 2b plus 1. Which gives us 2a minus 2b equals 1. Which gives us a minus b equals 1/2. You follow the algebra there?
Mm-hmm.
Yes.
Yes, okay. Since a and b are integers, a minus b is an integer, right? But a minus b equals 1/2 is not an integer. So we have a statement that says a and b are and are not integers. That statement is obviously false. You see this statement?
Yeah. What are your arrows?
That's what you demonstrate. So you have an arrow pointing that way and an arrow pointing that way when you demonstrate that you've come to a contradiction. You're saying, here's my impossible statement. Okay? You good?
Yes, keep going.
Well, I can't keep going when you're not looking.
Well, remember to look.
So
I'm
that
listening, I promise.
I can be sure that you're understanding.
Okay.
So are you good with this?
No. Yeah.
Okay?
Wait, just number 5. I'm good with everything else.
Since A and B are integers, A minus B is an integer, right? But we just showed A minus B equals 1/2 is not an integer. So A minus B is an integer and A minus B is not an integer. That's our false. Right? That's our possible statement. So, therefore, no such x exists. So we started out, assume by way of contradiction that there is some x, that's both even and odd, and we showed that that's impossible. Therefore, there isn't an x that's both even and odd. Does that make sense?
Did we ever prove that an integer plus or minus another integer is always an integer?
No, that was one of the things I told you we were going to assume in the beginning. Is that the sum of two integers is an integer, the product of two integers is an integer, and then, of course, the difference of two integers is just the sum of two integers. A minus B is A plus B.
Right.
So, no, that was just an assumption that we made. We can prove that later if we want, but you need proof by induction to do that. We haven't gotten there yet.
Okay.
So that's a proof by contradiction. So let's do another proof by contradiction to get another feel for this. So let A and B be integers with A not equal to 0. Then there is at most one integer x such that ax plus b equals 0. So if you pick two integers A and B, there is at most one integer x that you can plug in there that makes that equation true. Okay? So the way that we're going to prove this is we're going to assume by way of contradiction that there are two integers that you could have plugged in that made it true. So assume by way of contradiction that there is an x and a y such that ax plus b equals 0 and a y plus b equals 0, but x and y aren't the same thing.
Right, okay.
You good with that?
Yes.
Alright. So then ax plus b equals ay plus b, right? Because they're both equal to 0. That equals 0 and that equals 0, so those two things are equal to each other. Ax plus b equals ay plus b. Subtract the b's from both sides. Divide both sides by a. Contradiction. We assumed that there were two integers, x and y, that aren't the same thing that make this true. And we got that they are the same thing. You can't have x not equal to y and x equal to y. That's impossible. Therefore, no such x and y exists. So that this equation cannot have two unique solutions.
So, okay, that's so weird. I barely just clicked. So we're proving it by contradicting the opposite of it.
Yes, so here's another way to think about it.
That's so strange.
What is a contradiction of a statement?
The opposite of that statement.
Yeah, so how do you define contradiction? How do you define contradicting statements?
It's a statement that makes another statement false.
One statement is true and one statement is guaranteed to be false. That's contradicting statements.
Yeah.
The contradiction of all ducks are white is not that all ducks are black. Those are not contradicting statements.
Right.
Those are contrary statements, but they're not contradicting
There is
statements.
a duck that is black.
They are
The contradiction of all ducks are black is at least one duck is not black.
Right, but if your statement is all ducks are white and all ducks are black,
Those are not contradicting.
how are they not?
Those are contrary.
They're both true statements.
They're not both true statements.
Dude, contradiction means one is, if two statements are contradicting, that means one is true and one is false.
Yeah. So if all ducks are white and all ducks are black, one of those is true and one of those is false.
No, because you
What
can
if half your ducks are white, half are black? What if all your ducks are yellow? Both those statements are false.
Okay.
So
that's
contrary statements can't both be true. Contradicting statements are one is guaranteed to be true, one's guaranteed to be false.
So if one of those was true, then the other would be a contradiction.
No. Just because it happened to be true in some weird circumstance doesn't make it the case. We did the contradiction. It's the not. The not of all for all D in A, D is black, right? If we do the not of this statement, how do we do it? We we say there exists D in A,
So
where
instead,
D is not black. That's the contradiction.
Right.
It's a well-defined thing. There's one and only one contradiction of the statement. There's not many.
Really?
Yeah.
Okay.
It has to be well-defined, otherwise we can't have a mathematical notion of it. The contradiction of a statement is a well-defined thing. The contradiction of A is not A. That's its contradiction.
Couldn't many things show that though?
What do you mean by that?
So what I mean is, just looking at this breakdown here, instead of y, there could be another integer z, and it would prove the same thing.
Instead of Y,
You could use a different integer, it would prove the same thing.
could have used a different integer to prove.
Sorry.
I didn't use a particular integer
No,
down here.
you used all of them.
I didn't use all of them. I used any integer that's not x, is what y is. Y is an integer that's not x. That's the property of y.
Okay.
What integer is that? That's a weird question to ask. That's almost like asking what's x? It's a variable. What's y? It's a variable that's not x.
Okay.
That's what y is. So there's one and only one contradiction of this statement. The statement is, there is at most one x such that that's true. What's the contradiction of that statement? There is more than one integer that makes that true. That's its contradiction. So we show that its contradiction
Hang on, could
or
you-
not be
There is
led to
no.
something impossible.
There is no integer.
No, this says that there could be none. This is saying that there's either none or one. That's what the statement's saying. Pick two, give me an A and give me a B.
1, 2.
1 plus x times 2 equals 0. There's no x. That makes that true. Did I write it the same way or did I write it different?
It's fine. Whatever.
Ax
As long as x is an integer.
1x
Oh.
plus b, not b, 2.
I see.
So when this is your A and B, there is no x. But if you happen to pick, oh, in this case it is true. Right? Negative 2. Negative 2 is the x that makes it work. Plug in negative 2 for x. Right? Plus. Even if it's minus, it still works. But if you would have picked like 2x plus 3 equals 0, this one has no solutions. So they're saying if you have it of this form, integer times x plus integer equals 0, then there's either no solution or one solution. But there's never two solutions. This
I
has,
swear that is not true.
give me an example.
A is 1. No. A is 5. B is 6. X is.
There isn't an x that makes this true.
Oh, it's times. That's why.
Yeah. So there's either one x that makes it true, or there's no x that makes it true. That's what we were proving.
What's the 1x?
Well, in this case, there's no x. In this case, there's no x. In this case, there was one x. What we're saying is you can't find integers a and b where there's two numbers x that you could have plugged in there.
Oh, okay.
Or 3, or 4, or 5.
Right.
So we're proving that there's at most one integer solution to this. Maybe there's no solutions, but there's at most one solution. What's the contradiction of that? That there's 2 or 4 solutions. So we assumed by way of contradiction that there were at least 2 solutions, x and y, that are different. That led to a contradiction, that they were actually the same.
Okay.
Does that make sense?
Yes.
Yeah. I don't know what feels weird. I mean,
Nothing feels weird.
you understand what the contradiction of a statement is?
Yes.
Alright. So that's all the material that we had to cover for today.
Awesome, awesome.
So now let's really quick go over the test. So test on number 1, I wrote the answers on all your paper. Did any of you have questions about why a particular one of those was?
Will you define antisymmetric?
Yes, I did.
Antisymmetric. Antisymmetric is x related to y and y related to x implies x equals y.
Yes, I have a question. Sorry, yes. B and C.
B. So what property are you wondering on that?
Antisymmetric.
So show that B is antisymmetric. Okay, so on B, the relation is 1, 2, 2, 3, 3, 4, 4, 5. And we're doing this on the set. 1, 2, 3, 4, 5. So here's the relation that we're talking about. Here's the set that we have the relation defined on. And I said that this is antisymmetric, right? So I'm saying anytime you have x related to y and y related to x, you have that they're equal. Right? So find me a case that doesn't work. Find me a case where x is related to y and y is related to x, but they're not the same number.
All of us.
Well, if we have 1 related to 2 and 2 related to 1, we don't have that. So false implies anything is true. If we have 2 related to 3 and 3 related to 2, we don't have that. So false implies anything is true.
What? That makes zero sense, Murder.
It is vacuously true. There's no cases to check. We never had x related to y and y related to x.
We could have it in other freaking scenarios.
But not in this relation. This is a relation. For
So
any x,
all of them that don't have it also have it? It makes no sense.
the relation has a property, unless you can prove otherwise, is one way to think about it.
So
Every
basically,
time I had 1 related to 2 and 2 related to 1,
the only way
they were
you
equal.
can have antisymmetric is if it's the 1, 1, 2, 2, 3, 3, or if it's anything else.
If it's not symmetric, or if it's not symmetric, or it's symmetric and they're equal. If it's not symmetric, this is always false, right?
Yes.
Or, well, that's not even true. Because if I just add one thing in here, then it's not antisymmetric anymore. Right? If I come along and I add 2, 1, then it's no longer antisymmetric. Because I have 1 related to 2 and 2 related to 1, but 1's not equal to 2.
See, that's my question.
So that is what would make it no longer antisymmetric.
Okay.
So that's a fair way to say it.
Huh, that's
What I was saying before wasn't true. I was thinking about the individual element, not the whole set. So anyways,
Okay. So antisymmetric is a tricky one.
yeah, it's the weirdest of the 5 for sure.
Yeah.
So is there another one that you need to look at?
Yeah, the transitive one on C.
The transitive one on C. So that same set. Oh wait, not the same set. So 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. So let's write that one out. So we're looking at the set 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. And this one is transitive.
Yep.
So what's transitive? X related to y and y related to z implies x related to z, right? So anytime you have x related to y and y related to z, you have x related to z. Let's look at it. So I have 1 related to 1 and 1 related to 2 implies 1's related to 2. Yep. Let's see.
What? Hang on. What?
Pick an x. And you have to pick a left-hand element.
So y can be the same thing as x.
Sure. You already knew that because you said that the one that looked like this, 1, 1, 2, 2, 3, 3, 4, 4, oops, 4, 4.
What did I say about it, huh?
You said it was transitive.
No, I didn't.
Oh, you didn't?
You wrote transitive on there,
Oh,
but
you should have.
Okay, see, that doesn't make sense. See, I was thinking, okay, I only see two different freaking, I only see X and Y, so there's no Z's.
Okay, even if you think about it that way. So say y can't be the same as x. Okay? So anytime I have 1 related to 2 and 2 related to, I never have 2 related to in this, alright? Only 1's related to something. So this comes out false. False implies anything is true. True.
So dumb.
It's actually pretty cool.
No, it's not. Okay.
It's just hard to think about until it
Okay,
makes
I
sense.
see that now, but also like, it doesn't work in some cases.
I don't know when it doesn't work.
1 is related to 2.
And 2 is related to what?
Huh?
And 2 is related to.
Oh.
Ah. No, we don't have 2's related to 1 up here.
We don't have anything.
We have 1's related to 2.
Right?
So if you want x and y to be different, then you're going to get false implies is true. If you allow x and y to be the
Basically,
same.
it's gonna be transitive if there's any of them that have 1, 1 or like
If you
X, Y,
can't,
or equal.
if you can't find an x, y, and z that make it false, then it's true.
What?
Pick 3 numbers, 1, 2, and 3. Pick 3 numbers out of here. Or the same number 3 times, doesn't matter. Just pick a number for x, pick a number for y, pick a number for z.
2 is related to 3 and 3 is related to 4.
2 is not related to 3, so that doesn't do anything.
You said pick any numbers.
I know,
Boom,
so
I just found
2
a
related to 3
combination, now
is
it doesn't
false.
work.
Look,
So dumb. Makes me cringe.
I can tell.
False implies true, it hurts my brain. Okay.
Hurts until it doesn't. You gotta keep thinking about it until it makes sense, because it makes perfect sense.
I know it does.
Okay, any other ones?
No.
Okay, so move on with problem 2. Problem 2.
Do you want a homework, by the way?
Oh, yeah. I will want your homework. So, problem 2. Prove if x and y are even, or odd, I guess it doesn't matter which one we do first, then x is congruent to y mod 2. Right? So I'll start off 1, let x, y, and z such that x and y are even. 2, then there exists a and b and z such that x is equal to 2a and y is equal to 2b. We're going to skip the divides by 2. You know how to do that. 3. Then, let's see, we want x minus y is equal to 2a minus 2b is equal to 2 times a minus b. 4. Therefore, 2 divides x minus y, which gives us that x is congruent to y mod 2.
Oh, I should have done that way.
Yeah, we went on a huge mess.
Yeah, I
That eventually came back to this.
Yeah, I did the same thing, but it was...
I know you did the same thing, but you took like 8 steps in between. You're like, consider where we're trying to get, reverse all the way back to the beginning, and then say, and by the way, that thing I found over here is a C that you used. You made a big mess of it. And then if we change this to odd, then that makes this odd, and that makes this 2a plus 1, and that makes this 2b plus 1, and then x minus y is equal to 2a minus 1,
Still
or plus 1, sorry.
Minus 2.
Minus 2b plus 1. which again is just going to give you 2 times a minus b and c of b. So, not a huge difference between either of those proofs. Very similar thought process. That's how you do it. The success one, I think you all understand it's 5 factorial over 2 factorial.
Yeah.
Anyone not understand that? Anyone? Anyone? Alright, number 4, not a problem. Number 5, we happened to do right before class started, so you were all good with that. Number 6, I think you all got right. Alright. Number 7. Okay, number 7. You guys got a little weird all over the place. And...
How many groups?
Huh?
So there's groups.
I know. The question is, do you guys know?
No.
That's the problem, so we gotta fix that. Alright. So let's see. Let R equal the set of all ordered pairs such that x and y are integers and the absolute value of x is equal to the absolute value of y. Right?
Okay.
Prove that it's
Now we're going to prove it's an equivalence relation. Right? R is an equivalence relation. 1. First we need to prove it's reflexive. How do you prove a relation is reflexive?
no.
You show that for any x in the set that this is defined on, what set is this relation defined on? The integers. So I need to show that for any integer, call it x, call it y, call it w, call it whatever you want, x is related to x. So 1, let x in R, not real number, sorry. Not R, in Z, sorry. Let x be any integer. Now we need to show that x is in here. Or that x is related to itself, right?
Man, I did that differently.
2. Yeah, yours was all over the place. I went back to 2, but then I realized it was only half of the problem to the whole problem, so you only got minus 1. That's why I scribbled out minus 2. Anyway, observe that the absolute value of x equals the absolute value of x. Whoa!
Wow.
Which gives us that x is related to x.
Crazy.
3. Therefore, R is reflexive. 4. Now we need to show it's symmetric. How do you show it's symmetric?
Actually, it's y right here.
Yeah, you show for any 2 integers x and y where x is related to y, then y is related to x. So now we need that. Let x, y, and z such that x is related to y. Good? Then that means that the absolute value of x is equal to the absolute value of y, which gives us that the absolute value of y is equal to the absolute value of x, which gives us that y is related to x. 6. Therefore, symmetric. And then very similar for transitive. To show transitive, we start out with 3 integers, x, y, and z, where x is related to y and y is related to z. So, let x, y, and z in the integers such that x is related to y and y is related to z. What does it mean for x to be related to y?
X has the same absolute value as y.
Right, then the absolute value of x equals the absolute value of y, and the absolute value of y equals the absolute value of z, which gives us that the absolute value of x equals the absolute value of z, when you substitute in, which gives us that x is related to z. Therefore, it's transitive, therefore it's equivalence relation. Any questions on that? How you start these out kind of gets you going. Don't be lazy about stating stuff like this, stating stuff like this, stating stuff like this. It breaks down your thinking.
Yeah, it makes sense.
Because you find out really quick when you don't do stuff like that, you stop making sense. If I don't get a new x and y to kind of hit restart here, here's the only x I ever talked about, and now I'm suddenly talking about it over and over and over again. Right? You can kind of do this as breaking up into 3 proofs.
Yeah.
Cleans it up.
So don't be lazy about stuff like that. And then B, I don't know, I think you guys all got B.
Yeah, that was pretty simple.
Pretty simple. And then 8, I don't know why everyone gets this. Because we just went over this a gazillion and a half times. So let's go over a gazillion and a half and 1. What's the binomial theorem? Binomial theorem, x plus y to the n is equal to the sum from k equals 0 to n of n choose k, x to the n minus k, y to the k. Alright, and let's see. We were doing x plus 2 to the 50, looking for 17. So we had x plus 2 to the 50, and we were looking for the coefficient to the term x to the 17. Right?
Did you drop me 2 or 1?
I don't know.
I can't tell.
You docked me too.
2.
Should have been 1.
I thought about it, and then I'm like, no, that's too big of a mistake. So then I bumped it up.
All I did do was write 2 for y.
Yeah, I thought it was a pretty big thing, not plugging
Wait a
in
minute.
Y.
Is that what? Keep going, I'll figure it out.
Alright, so now we have this, and we're plugging in, what's our k? 33. So now write this out with k equal to 33. So we've got 50 choose 33 times x to the 17, y to the 33. Wait, we don't have a y. What do we have?
2.
We have a 2. Ah.
I knew it.
Which then gives us that our coefficient is 50 choose 33 times 2 to the 33.
I forgot that. Dang it. I was
How
so
much
close.
does this problem worth?
5 points.
Every problem's worth 5 points.
And you dropped me 2 out of 5.
I know.
I
was
also
so
worked right.
close. Like, how did I forget that?
I think I also docked you because what you wrote down wasn't a coefficient.
This one here.
Yep, it's because you included the x, otherwise you would have got minus 1.
What? I got mine assuming. I didn't write it as an
My
X.
bad.
I just substituted.
Yeah, that's true. I'll give you one more for that.
So did you not look at this?
I did. You didn't go in there. Okay.
Do you want to do it?
We don't have time. That's class. So give me back your test. Give me back your homework. And
Maybe that's not my proof upstairs.
Yeah.
that combinatorial proof.
Yeah, the homework that you said to do.
Oh, yeah, we can go over whatever problems you want. So this time I'll keep these so I don't lose your speaking scores.
But only
Wait,
for a little
don't keep
while.
it forever. I want
Yeah.
it mine.
Oh, I'll give it back next week. I just
Okay.
Trust
put
me.
them in.